So good morning, students. So today I'll discuss hydrodynamic lubrication. So what is this hydrodynamic lubrication? So this hydrodynamic lubrication, it is observed in case of journal bearings. So journal bearing means a journal is a shaft which rotates at higher RPM, and it is being surrounded by a bearing block, and the space which is between the journal and the bearing is filled with a proper lubricant. You can see a schematic diagram of the journal bearing over here. So this shaft is considered to be a journal, and it is surrounded by a bearing block. In the side view, you can observe this journal is having a radius of r, and this bearing will have other radius, and the gap between the inner radius of the bearing block to the outer radius of the journal is filled with a lubricant. So this is called clearance. This is a schematic view of a journal bearing, and these journal bearings are meant for carrying loads, high loads. Okay, so this when this journal rotates at some RPM, due to the hydrodynamic action which is created between the convergent and divergent fluid film within the bearing is sufficient to lift the journal, and the journal runs concentrically with the bearing block. Okay, so this kind of lubrication is called hydrodynamic lubrication. Mainly it is observed in case of journal bearings. So in order to calculate the load carry capacity of the this journal, so Petrov is the name of the person. He has developed an equation for lightly loaded bearings. See, in the design of machine elements 2, you might have studied about the heavily loaded journal bearings and lightly loaded journal bearings. Petrov is the person who derived the relevant equations for lightly loaded bearings. We shall see that derivation, and using the formulas which are obtained by the derivation will solve the related problems. Okay, so this is a schematic view of the journal bearing, and this is the expanded, developed view of the journal bearings. So just look at that. Bottom surface represents the bearing block B, the bearing block. The above surface, see, when this journal is a section, okay, just imagine it is developed. You have done development in drawing. It's a circular cylinder. When it is developed, it looks like a rectangular plate. No, similar way. So when the outer block is developed, it takes the shape of the rectangular object, and similarly, when journal is developed, it takes the shape of the rectangular object. So the front view is shown over here. Uh, the bottom surface B represents the bearing block, which is stationary, whereas the above surface A represents the journal surface, which will be rotating at some RPM, and it will be having a velocity u. Okay, and this gap, we call it as the clearance. That is the height h, distance between upper surface to the lower surface. And when the cylinder is expanded, so this dimension is 2 pi r, this 2 pi r dimension. So develop the journal bearing surface for journal bearing with the journal running concentrically with the bearing. So this is the condition subjected to journal running concentrically with the bearing. See, there are some conditions for this. When journal runs concentrically, it has to satisfy some condition. So we shall see that condition now. So consider this concentric bearing as shown in the figure. A journal will run concentrically with the bearing only when there are three conditions. I'll just state those conditions now. The radial load acting on the journal is equal to 0. The radial load acting on the journal, that is equal to 0. So no load condition. So this journal runs concentrically with the bearing in case of no load condition. Second one, the viscosity of the lubricant is very high and tending to infinity. So second possibility is the lubricant which is there between the journal and the bearing block will have viscosity, infinite viscosity. Third one, the speed of the journal is infinity. So the speed should run at infinite speed. Okay. So see, all these three cases are not practical. What are those cases? There is no load at all. See, if there is no load, then no use of using this bearing. Okay. So and also this shaft will have its own weight, self weight. So you cannot consider zero load condition. Second condition, what is that? The viscosity of the lubricant is infinite. So you cannot have a lubricant whose value, viscosity value is infinite. And third condition, the shaft should rotate at infinite speed. And this is also not practicable. So all these three conditions are ruled out. But what happens, however, the load which is light enough, the load, if the load applied on the journal is very light, light means you can consider less than 1 kilonewton. So the loads which are applied on the journal which are less than 1 kilonewton can be considered as a light load. And also in the second criteria, that is the journal has sufficient high speed. Suppose if it is running at sufficient high speed means it could be probably 3000 rpm, 4000 rpm like that. So more than 2000 rpm generally we prefer. So in that case, journal starts rotating concentric with the bearing. So not to the condition of infinite speed. Third condition, viscosity. Viscosity is sufficiently high, not infinite. So considering these three conditions, this journal can run concentrically with the bearing. Okay, so we'll assume these three conditions which are practicable. What are the conditions which are practicable? The load is light enough, the journal has sufficient high speed, and the viscosity is also sufficiently high. So these three conditions are practicable. So considering these conditions, we will derive the required equations. Okay. So in order to have a derivation, so you consider the geometry of the bearing. So that is L is the length of the journal, that is shaft. D is the diameter of the journal, and C is the radial clearance, and the capital C is the 2C diametric clearance, and the psi is equal to C over D. That is the ratio of diametrical clearance to the radius of the diameter of the journal. So that is called diametrical clearance ratio. So diametrical clearance is 2 times of that of the clearance, 2C. And n dash is equal to n over 60, that is in RPS, revolutions per second. So developing the journal and the bearing surface with the journal running concentrically with the bearing as shown in the figure, in which it represents journal moves with constant velocity u, and B represents bearing surface, that is stationary surface. And also assuming that the viscosity is constant throughout the oil film and the frictional force F mu. So consider F mu is the frictional force induced in the journal resisting the relative motion, and this frictional force is given by F mu is equal to tau into A, where tau is the shear stress and A is the area of cross section. And also, previous class I have discussed about Newton's law of viscosity. So from the Newton's law of viscosity, this shear stress tau is given by tau is equal to neta into u over c, where neta is viscosity. See, in some textbooks or in some other study materials, they have used the Greek letter mu for representing viscosity. Okay, it is left to them. So you can use a neta also, and you can, in the meantime, you can use mu also to represent viscosity. Nothing wrong in that. So in this study material, we have used neta to represent the viscosity of the lubricant. So using this relation, that is F mu is equal to tau into A. This is very simple. So tau is equal to force by friction of force by area. Then the force is equal to tau into A. That's it. Okay. So substituting this tau value into this equation, so F mu becomes neta into U over C into A. Okay. And we know that velocity U is equal to pi dn by 60. And in turn it is equal to pi d n dash, where n dash is n over 60. where n dash is n over 60. So that is in rps. So this velocity is in rpm, revolutions per minute, and this is in rps, revolutions per second. Okay, and area. So area is equal to pi dl. When the cylinder is expanded, so it takes the shape of the rectangular sheet, as I told. So that is pi d, the perimeter, and L is the length, height, or height of the cylinder. You can consider. So area becomes pi dl. That is area of the lubrication, and radial clearance C is equal to C by 2. This is already stated in the geometry. Okay, C is equal to capital C over 2. So substituting all these values means U, A, and C into this equation, F mu equation. So we get frictional force F mu is equal to neta into pi d n dash into pi dl over capital C over 2. So further simplifying the above equation, for above formula, so we will get an expression for frictional force, that is F mu is equal to 2 pi square neta n dash d square L over capital C. So call this as equation 1, and this equation 1 is known as Petrov's equation for frictional force. And this equation is available in the data handbook. Okay, so you can refer data handbook by Mahadevan, or you can refer data handbook by Lingaya. So where these formulas are available, and even in the design of machine elements too, also we had a separate chapter for lubrication and bearings. There we have used this similar equation. Okay, so this equation one is called Petrov's equation for frictional force. Next, equation 1 then frictional torque. So soon after determining the frictional force, so now since the journal is rotating subjected to torque, so we can develop an equation for frictional torque also. So as you all know that the torque is nothing but it is the force into perpendicular distance. Okay. So in case of frictional torque, it is frictional force into perpendicular distance. Perpendicular distance is nothing but the radius. Okay. So the outer, you can just assume that a shaft, and the load is applied on the outermost motor line of the shaft. So that frictional, the torque which is applied can be calculated as the force applied into perpendicular distance to the axis. Okay. So axis means radius. We have developed the equation for F mu. Just make use of that equation. And also we know that this radius is half of the diameter. So put that value and just simplify this formula. So you will get the formula for frictional torque. Very simple derivation. Okay. So just putting this F mu value in this formula and putting R in terms of diameter. So simplifying this, so we'll get the equation for frictional torque, that is given by pi square neta n dash L d square over psi. So you call this as equation number 2, and this equation number 2 is known as Petrov's equation for frictional torque. So in the examination, you may get a question. Okay, so derive Petrov's equation for frictional torque. So what you have to do, you cannot just simply say frictional torque is given by F mu into R. So you have to derive equation for frictional force first. Okay, so this derivation up to here from this point to, so you have to state the condition for concentric running. Okay, stating the limitations of concentric running and how it can be overcome. You have to state all these things first and draw a neat sketch of this journal bearing and show the expanded view, developed view. This is section view and this is the developed view. Okay, soon after stating all these things, so geometry, let's assume the geometry. L is the length of the journal, D is the diameter of the journal, radial clearance, capital C is the 2C, that is diametrical clearance, and the psi is the ratio of capital C by D, that is diametrical clearance ratio, and n dash is n over 60, that is an RPS. Okay, so after deriving the F mu, so you can derive mu t, that is frictional torque. Okay. Huh. Then after finding the frictional torque, so now you can derive an equation or a formula for coefficient of friction. Okay. See, as we are all know that this consider body. Okay, just to demonstrate what is this coefficient of friction, I'll just take the help of this picture. Okay, so this here it is a body which is sliding over a surface, and force F is applied to that body. Okay, and this body will have its own weight. This body will have its own weight, and this coefficient of friction mu is given by, it is a ratio of F, the force being applied, to the W. Okay, so then F mu is equal to mu into W. W is the load, weight, or F is the force applied. Okay, so just what I do is I need the expression for this mu. I need is this expression for mu, that is coefficient of friction. So I will make use of this torque expression, considering the torque expression. So mu t is equal to F mu into R. So substitute the formula which is obtained for torque, that is frictional torque, and also so just replace this F mu with mu into W, where mu is the coefficient of friction and W is the weight, and also replace this R by diameter. Okay, and and rearranging this formula, and taking mu on one side and remaining on the other side. So dividing the common just okay, and also this pressure P is equal to load by perfected area. Okay, so we are all know that load is equal to pressure is equal to load by area. So area means L into D. That is rectangle. Okay, so when it is open, no, the journal is open, this becomes L into D. So W is equal to P into L into D. So just replace this W by P into L into D, and further simplifying this, taking mu on one side and the remaining thing on the other side. So this equation is simplified, and we'll get an equation that is mu is equal to 2 pi square and eta n dash over P into 1 over psi. So we call this as equation 3. And this equation 3 is called Petrov's equation for coefficient of friction. Okay, this mu is called Petrov's equation for coefficient of friction. So with this derivation, we derived expression for coefficient of Petrov's equation for frictional force, Petrov's equation for frictional torque, and also Petrov's equation for coefficient of friction. So whole thing, this can be asked for 10 marks. This whole derivation up to coefficient of friction, so you may get it for 8 to 10 marks. Okay, so just if it is asked for torque, you leave this expression at this stage, you leave this derivation at this stage. If it is just asked for frictional force, leave this derivation at this stage. Okay, so accordingly the marks, how much of marks it is allocated, you just derive accordingly. Okay, so with the so derived formulas or equations, we shall see one problem, and also one more important thing. So ultimately, you have to calculate the power loss, because whenever a journal carries a load or it is rotating at some RPM, okay, due to the frictional force, due to the friction, some power is lost. Okay, so that the power input may not be equal to the power output, so you have to calculate that the power loss. So in order to calculate the power loss, so one simple formula is available. So power loss N is equal to frictional force into velocity. So force into velocity. So what is the unit of force? It is Newton. What is the unit of velocity? Meters per second. So the friction of power loss becomes Newton meters per second. And we are all know that Newton meter is joule. Newton meter is nothing but joule. Joule per second is watt. Okay. If you divide this expression by 1000, this power loss comes in kilowatt. So this equation 4 is called as Petrov's equation for power loss. Clear? So you got the expression for power loss, and all these expressions, that is equation 1, 2, 3, are all available in the data handbook. You can just refer the data handbook and fetch the details. Clear? And from the above equation 3, which is that equation 3, this is the equation 3. From the above equation 3, it is clear that for the bearing with the fluid film lubrication, the concept of lightweight bearing includes not only the load but also the elements such as the speed of the journal, viscosity of the lubricant, and clearance. However, we can define a lightly loaded bearing as one in which the eccentricity of the journal is so small that the Petrov's formula give good approximation for frictional force and frictional losses. And also the coefficient of friction for a given bearing is variable, which is inversely proportional to the load and directly proportional to the journal bearing. So just observe the coefficient of friction, inversely proportional to the pressure load and directly proportional to the speed. Mu is directly proportional to the speed and inversely proportional to the load. Load pressure is equal to load by area. Okay, so that is mentioned over here. And for the lightly loaded bearing, having a high speed would have a relative high coefficient of friction in spite of correct design and satisfactory performance. So these are all the comments of the so derived equations. Okay, so you can also have a comment on that. After derivation, just to show two, 3, 4 comments of the given so derived formula that gives you the more meaning to the derived formulas. Okay, and I will take up on a simple problem related to lightly loaded journal bearing. All of you just take this problem, and I may ask any one of you to read the problem. Who is okay? Shivdas, are you there? Shivdas, Shivdas, can you hear me? Praveen Totigar.
Yes, sir. Answer.
Oh, okay, fine. Praveen, just read this problem.
A lightly loaded journal bearing has the following specification.
Sir, continue.
Diameter diameter of
Diameter of
journal
journal. Hmm.
50 mm,
Hmm.
bearing length 80 mm,
Hmm.
diametrical clearance ratio
Hmm.
0.002,
Hmm.
radial load 750 Newton,
Hmm.
viscosity of lubricant 10 cp,
Hmm.
speed 400 rpm. Determine torque
4,000.
on the journal,
Hmm.
coefficient of friction, power loss.
Hmm. Power loss. Very good. Thank you. So a lightly loaded journal bearing. So they have mentioned that a lightly loaded, and it has got the following specification. Diameter of the journal is 50 mm, and the bearing length is 80 mm. L is 80 mm, D is 50 mm. Diametrical clearance ratio, that is psi, that is, it is capital C. It is a ratio of capital C to the D. It is 0.002. Radial load 750 n Newton. So as I said, normally generally we shall consider lightly loaded means shaft should withstand the load below 1 kilonewton. So here it is 750 Newton. So you can consider it as lightly loaded. And the viscosity is given, that is 10 centipoise. So convert that to SI unit. So just remember that if viscosity value is given in centipoise, okay, so in order to convert that to SI unit, just multiply with 10 raised to minus 9. So conversion, I can discuss this from CJ system to SI system, okay, but it's very simple. So just multiply by 10 raised to minus 9 Newton second per, it converts to Newton second per mm square. And speed. In few cases, directly they will give it in Pascal second. Okay. So if Pascal second means Newton per meter square second. Okay. So in here you are converting it to Newton second per mm square. Newton per mm square second. So mm means everything is in mm. Generally, diameter is in millimeter, length is in millimeter. So I will convert that viscosity to Newton second per mm square. And n is given 4000 rpm. So your n dash you can calculate. Just divide this 4000 by 60. So you'll get n dash in rps 66.67 rps. So first you have to find frictional torque and coefficient of friction and ultimately the power loss. So we have Petra's equation. So just to recall the derived equation, you can only two ways you can learn. So the first way is easily you can remember this formula, very simple one. Otherwise, you may refer the data handbook. So taking that formula from the data handbook and substituting uh, the parameters over here. So everything is known. Just to substitute that and calculate coefficient of friction, torque, frictional torque. Similarly, so you can calculate the coefficient of friction. So coefficient of friction formula is mu is equal to 2 pi square into neta n dash over p into 1 into in 1 over psi. So p value, is it given over there? P value? P value is not directly given. Instead, they have given you the load 750 Newton. And we know that this P is equal to W by LD here in the derivation. W is known to you, length is known, diameter is known, you can calculate pressure, not an issue. Okay. So calculate that pressure P. This is required for this formula, and just to substitute that and calculate it. Okay. Ah. So I will give you 2 to 3 minutes to calculate the coefficient of friction, and I may pick any one of you to say the answer. Okay. So I'll just give you 2 3 minutes. Just to put the value relevant value over here and calculate the coefficient of friction. Psi is psi value. Take the psi value 0.002 and neta, that is coefficient viscosity, 10 into 10 raised to minus 9, 10 into 10 raised to minus 9, and n dash 66.67, n dash 66.67, psi is 0.002, p calculate, p is load by area, that is W by LD. L is 80 mm, D is 50 mm. So pressure is 0.1875 megapascal, that is newtons per mm square. So calculate the coefficient of friction. So take p value. I will give you the p value also directly. 0.1875 megapascal. Substitute all this value into this formula equation and calculate mu. Oh, okay. Mm, Anish, Anish AP, did you get the answer? Mohan, Praful, Praful. Okay, I will tell you the answer now. So mu is equal to, just to substitute the value and calculate. That's it. 0.033 is the coefficient of friction. And similarly, calculate the power loss. So in order to find the power loss, you need F mu value, that is coefficient of force friction. Frictional force. Just make use of that formula. Calculate the frictional force. Just a substitution and calculation. That's it. And similarly, okay. So power loss is coming to be 0.275 kilowatt. This is the power loss. Okay. So I will stop at this stage. So I will take up one more problem in the next class, and I will discuss. So just put your USN in the chat box. 23 have given their attendance. Remaining, if you are missing, if you have missed that, put your USN in the chat box. So we'll end the session for today. Thank you. Thank you one and all. We'll meet again in the next class.